Hi everyone, I am Jemima Verduello, and today we will dive into a fascinating world of robotics by exploring a classic, simple, and super cool project, and that is line following robot. We will look at its design and how all the parts are connected and the smart instructions to make it move. First, let's break down the physical design of this robot. As what you see on the screen, it shows all the connections. But don't worry, we will go through it step by step. The brain of this robot is the board right here. It is called the Arduino. It is the microcontroller that receives program instructions and sends commands to the rest of the robot. This robot follows a line using its eyes, which are these 5 infrared sensors that is mounted in this blue sensor module. They are essential for detecting the black line. Each sensor is connected to a specific analog pin on the Arduino. The leftmost sensor is connected to A0. The next sensor is connected to A1, and the middle sensor is connected to A2, and the slightly right sensor is connected to A3, and finally, the last sensor is connected to A4. To make a robot move, we use 2 DC motors to control their power and direction. We have this board featuring the L293D driver. This chip acts as the bridge between Arduino's low power signals and the motor's higher power needs. We have 2 separate motors, one for the left and one for the right, which allows the robot to steer precisely. Let's look at how the motor driver receives commands from the Arduino. For our left motor, its speed is controlled by the ENB pin on the motor driver, which is wired to digital pin 9 on the Arduino. The direction of the left motor is controlled by 2 pins, IN3 connected to digital pin 10 and IN4 connected to digital pin 11. Similarly, for our right motor, its speed is controlled by the ENA or the Enable A pin on the motor driver, connected to digital pin 6 on the Arduino. And its direction is controlled by IN1 connected to digital pin 7 and IN2 connected to digital pin 8. We also have right here a simple control for our robot's operation, the 2 push buttons. The start button is connected to digital pin 2 on the Arduino, and the stop button is connected to digital pin 3. When pressed, these buttons send a signal to the respective Arduino pins telling the robot to begin or end its movement. For power, Arduino typically receives a 5 volts via a USB connector or a separate power adapter. The motors requiring more current are powered by a dedicated 7.4 volts, which connects to the motor driver via a convenient slide switch, allowing us to easily turn the motor power on or off. This setup ensures stable power delivery to both the control electronics and the drive system. With the hardware explained, let's now dive into the brains of the robot, the Arduino code. This is where we define the robot's intelligence and how it reacts to its environment. Let me show you the code on the screen as I am explaining it. So we begin by assigning clear names to our sensor pins using constants. This makes the code much easier to read and understand. IRML means most left sensor, the IRL left sensor, IRC center sensor, IRR right sensor, IRMR is the most right sensor. Next, we define the pins used for motor control, again with descriptive names. Notice these correspond to the L293D driver pins. ENA and ENB allow us to control the speed of the motors using pulse width modulation or PWM. The IN pins determine the motor's direction of rotation. Our start and stop buttons are also assigned their respective digital pins. We have 2 key variables here, running, a boolean that indicates if the robot should be actively moving, and last move, an integer that stores the robot's most recent movement state to help it recover if it temporarily loses the line. The threshold value is crucial for sensor interpretation. Our IR sensors measure reflected infrared light. A black line absorbs more light, resulting in a lower analog reading, while a white surface reflects more, yielding a higher reading. This threshold helps the robot differentiate between the black line and the lighter background. Its exact value might need adjustment based on your specific line and surface. Now, let's examine the setup function. This code executes only once when the Arduino is powered on or reset. Here, we configure each pin as either an input for buttons or an output for controlling motors. We also ensure the motors are stopped at the start and begin serial communication, which is helpful for sending messages to a computer for debugging. Now next, move on to the loop function. It is where the robot's continuous operation resides. This code runs repeatedly, thousands of times per second, checking sensors and updating commands. The first part of the loop checks the start and stop buttons. The delayed 300 milliseconds acts as a debounce, preventing a single button press from being registered multiple times. If running is false, meaning the stop button was pressed, the robot simply stops and waits until the start button is pressed again. If the robot is set to run, it immediately reads the current values from all 5 IR sensors. Analog read returns a value between 0 and 1023, indicating the intensity of the reflected light. These analog readings are then converted into simple true or false Boolean values based on our threshold. If a sensor's reading is less than the threshold, it means it's likely detecting the black line, and its corresponding line variable becomes true. This section contains the core decision-making logic for our robot. If all sensors see white or no line is detected, the robot attempts to continue its last move. This is a common strategy to help the robot recover if it momentarily loses sight of the line, like at a small gap. If the center sensor is true, the robot executes move forward function. This is its primary state, directly on the line. If left or most left is true, this indicates the robot has drifted to the right, so it needs to turn left to get back on track. If right or most right is true, this means the robot has drifted to the left, so it needs to turn right to correct its path. If none of the above specific line patterns are met, the robot stop motor's function, indicating it might be in an unexpected situation or has completely lost the line. Finally, let's look at the simple functions that control the motors directly. Analog write takes a value from 0 to 255 to control motor speed, where 255 is full speed and 0 is stop. Digital write commands sent to the in pins determine the motor's direction. For example, high-low might make it spin forward, while low-high makes it spin backward. For turn left function, one motor might spin backward while the other spin forward, allowing the robot to pivot in place or make a sharp turn. The same logic applies to turn right. Stop motor simply sets the PWM values for both motors to 0, bringing them to a halt. So that's the detailed look to the line-following robot's physical setup and its intelligent code. By combining these components and programming them effectively, this robot can navigate a black line with impressive autonomy. Exploring projects like this isn't just about understanding electronics and programming. It's about problem solving, applying logical thinking, and seeing clever design come to life. I hope this explanation was clear and inspire your own curiosity in robotics. Thank you for watching this demonstration.